Okay, so this last section is just kind of mixing them all together using all the formulas. Some are in a different way, some are just to kind of combine and show the differences, verify. So just to wrap up Unit 6. So I went ahead and put typically the most commonly used formulas in those three boxes: independent, dependent, conditional probability, mutually exclusive, and not. And then I think I have 4 examples for us to try. Some have subparts, so. But just kind of to hit some problems that we might not have addressed prior, because there was just a lot of information in this unit. So example 1, it says when drug A and drug B are taken together, they operate independently. Drug A is effective 85% of the time. Drug B works 90% of the time. If both drugs are taken together, what is the probability that neither drug is effective? So what this basically is saying is we want that, how about A is not effective or fails or whatever, and B is not effective. Or you could think of that as probability of not A and not B, if you want to think of it simpler. Either way, doesn't really matter. So we don't really have any explicit information about that, so we need to do some interpreting. So what we know is that drug A works 85% of the time. So what that means is A does not work. Well, if we take off 1 minus 0.85 is 0.15, okay? Same thing with drug B. So drug B works 90% of the time. That's a pretty good one. And so that means that B does not work, or it's not effective, 10% of the time. Okay, and so we kind of know some information, but if we want not A and not B, then we are going to go up here, and it says they're independent. So we're going to look at this. So it doesn't matter if it's the not in front, because we can just apply that to the right side of the formula. So not A and not B would actually equal the probability of not A times the probability of not B. See how we can kind of apply that? And we really haven't kind of seen this concept before. So the probability of not A is 0.15 times the probability of not B is 0.10. So the chances that neither of them are going to be effective is 0.15 times 0.1, which is 0.015, which is really, if we multiply by 100, it's 1.5% of the time. And that should kind of make sense because both drugs are pretty effective. So to get them both to fail at the same time, it should be pretty little. Okay? All right, let's try a totally different example. Example 2, Vince buys a box of candy. We've got 6 chocolate pieces, 4 fruit flavored pieces, and 2 mint. He wants 3 pieces of candy, and he is not going to put them back. So we're going to act like he's selecting them one at a time. Find the probability that all 3 pieces will be the same type of candy. So really, we have some scenarios. I can have all 3 chocolate. Then I can also add all 3 fruit and all 3 mint. Okay, and so because we have different scenarios, that's when we would add them each separately. So within each of these, I'm going to have like a chocolate on my first, chocolate on my second, a chocolate on my third. And so because all of these are one experiment at a time, you would multiply these probabilities together. So without replacement, I've got on my first try, I can do 6 out of, I've got 6, 7, 8, 9, 10, 11, 12 pieces of candy altogether. Then I'm going to keep one of those chocolate, remember, and I got 5 chances out of 11. Keep my second piece of chocolate in my hand to make sure, and so I only have 4 out of 10 left. Then that would be the probability to get all chocolate. Now, We can also have all fruit though. So same idea. I've got 4 out of 12 plus, oops, not plus, times 4 out of 11. Oh, I really am having a hard time thinking and talking today. And then on my third try, I've got 2 fruit pieces in my hand, so 2 out of 10. All right, and then we could calculate all that. My last chance is I could get 3 mint. So on my first hand, I've got, I only have 2 though to pick from. So is it possible to get all mint in my hand if I only have 2 to pick from and I need to pick 3 candies? No, it sure isn't. So this is actually even not possible. So really you would just be calculating this. Okay, and you're welcome to type those in. I think showing you the work, I would even accept that as a full credit answer because typing it in shouldn't take much skill. All right, so that's the whole idea. Let's look at example number 3. A bottle contains 12 red marbles and 8 blue. 1 marble is chosen at random and we're not going to put it back. Then we're going to pick a second marble. So we're picking 2 without replacement. Compound probability. Determine the probability that at least one of the marbles is red. So what we can have is we can have the probability of 1 red and then 1 blue. And we would have to figure out if it's also 1 blue and then 1 red. Or we could have 2 red. So probability of 2 red. And since they're both red, the order wouldn't matter. Now, this is one option. I want to show you a different strategy though. So, because like, what if I would have had, if I picked 5 marbles, okay? So sometimes finding what you don't want and using the complement idea could be quicker, okay? This one's not terrible because it's just a couple to find, but they could get more involved. So we're going to do the opposite. We're going to do 1 minus what we don't want, which is the probability of no red. Okay. So that means if I want no red, I'm really looking for a blue and a blue. So think of it like that. Okay. And like I said, this would be more reserved if we were picking 6 marbles and you wanted at least 5 or at most 1, you know, things like that. So 1 minus, well, the probability to get a blue is going to be 8 out of, we've got 20. I'm going to keep that blue in my hand, so my second blue would be 7 out of 19. So see how that's just going to be much quicker, much simpler. I don't have to worry about does the order matter, things like that. And so what do we get? 1 minus, I'll just go ahead and finish this, 56. I should reduce, that's okay. 380. Yep, totally should have reduced. So let's see, what's that? Divide by 4, I get 2 out of 5. So 1 minus 14 out of 5. So then that gives us 81 out of 95. So it should be pretty high because we have more chances to get at least 1 red than we do to have no red. Okay. All right. And also, I don't think we've used the idea of a complement for a long time. So just good refresher. The last table I just want to kind of show and compare the conditional probability order and just regular probability. So they give us a frequency table and then they give us some ages and owning a truck or a car. So find the probability that they will own a truck given that they are 16 to 35. So remember, on conditional, I want to know when they both happen first. So a truck and 16 to 35, we've got 10. Out of, remember my total is always the given part, so my total is all the people that are 16 to 35. So we're going to go across and we've got 50. So 1/5. Find the probability that will be 16 to 35 given that we prefer a truck. So how many do they both happen at the same time? So 16 and 35 in a truck, it is still 10 out of given that they own a truck. So now we want the truck total, which is a total coincidence. So 1 out of 5. Okay, so depending on the values, they could be the same, but you notice we did use different values. Find the probability that they own a truck. So remember, this is how many own a truck all together out of all the people. So we get 250. And find the probability that they will be 16 to 35 years old. So we've got 50 there out of all the people total. Look at this, 4 different questions with the same answer. So just kind of a good review. So on your practice, you're just going to get random probability questions. So give it your best shot using some of these formulas from any section, okay?